Page 164, problem 62 is a 250-gram block is dropped onto a relaxed vertical spring that has a spring constant of K equals 2.5 newtons per centimeter. The block becomes attached to the spring and compresses the spring 12 centimeters before momentarily stopping. While the spring is being compressed, what work is done on the block by A, the gravitational force on it, and B, the spring force? C, what is the speed of the block just before it hits the spring? Assume that friction is negligible. D, if the speed at impact is double, what is the maximum compression of the spring? Now, the equation that we're going to be using is force equals mass times acceleration. Force of the spring equals negative K times displacement, and K is just a coefficient that's different for every spring. Kinetic energy K is equal to 1/2 mass times velocity squared. And work equals force times displacement times cosine of theta, and theta in this case is the angle between the force and displacement vectors. And work is also equal to change in kinetic energy. It's really change in any energy or transfer of energy, but in this case we're only dealing with kinetic energy. And work done by a spring equals 1/2 times K, the coefficient of the spring, times x naught squared minus 1/2 K times x final squared. The given information in the problem is that this green block is dropped on a spring, and there's these two blue balls on either side of the spring to show that it's not like falling over and like getting bent or anything funky like that. And they tell us that the block weighs 250 grams, which is 0.250 kilograms. I'm just going to simplify everything to like standard units here to make it simpler. Also, the coefficient of the spring, K, is 2.5 newtons per centimeter, which is 250 newtons per meter. The displacement when the block is dropped on the spring is 12 centimeters. I said it's negative because it's going down, and that is really negative 0.12 meters. And they tell us friction is negligible, so we don't have to worry about that. Part A, what work is done by the gravitational force on the block? Well, we're going to use the equation work equals force times displacement times cosine of theta, but since the force of gravity is pulling the block down and the displacement of the block is also going down, the angle between them is 0 and cosine of 0 is 1, so we can just cross that off. It's really not important in this part. The displacement we know to be 0.12 meters, and the other equation we're using is force equals mass times acceleration. We're going to use this equation to solve for the unknown force in the work equation. Now we know the mass of the block to be 0.250 kilograms. The acceleration is negative 9.81 meters per second squared, because that's the acceleration of gravity. Multiply those out, we get Fg, which is the force of gravity, equals 2.4525 newtons. And with sig figs, that's 2.45 newtons. Multiply that by displacement in the original equation. Remember, we don't have to worry about cosine of theta, because that is 1. And we get Fg times displacement equals 0.29 joules. Now, part B, what work is done on the block by the spring? The equation for the force exerted by a spring equals negative K times displacement. And we know the K is 250 newtons per meter. So, since the integral of force and displacement yields work, force times displacement, remember that's work, we can integrate the equation for the spring from 0 to its final x, which is negative 0.12 meters. So down here we've got the integration from 0 to negative 0.12 of the equation. Force equals negative times the k, negative 250x dx, and I took out the d and made it an x because it got confusing. There's like 3 d's in a row there, so x is just displacement in this case. And that equals negative 1.8 joules. Part C, what is the speed of the block just before it hits the spring? So first, we need to use this equation for kinetic energy. Also, we're going to use work equals the change in kinetic energy. Now, we know that the final kinetic energy, or we'll think of, as soon as it hit the spring, it's going to be moving, but whenever it stops moving, it's going to have a kinetic energy of 0 because kinetic energy factors into velocity and it multiplies out to be 0. So we can say that work equals the negative of the K initial, which is negative 1.8 joules, the work done by gravity, or the work done by the spring, plus the work done by gravity, since it's the opposite direction. And that turns out to be 1.5 joules. So yeah, cross off the kinetic final. And so we can just say that this 1.5 joules of initial kinetic energy equals work. And we plug in mass, which is 0.250 kilograms again, and solve for velocity. So we have 1.5 joules equals 1/2 times mass, which is 0.250 times velocity squared. We solve for that, and we get the velocity is negative 3.5 meters squared. It's really not when you solve the equation, but since it's going down, we're going to stay consistent and say that it is negative because it is moving down. Part D. How far will the spring compress if the block hit with twice the speed? Now, twice the speed is negative 7 meters per second, so that's what we're going to use for our velocity. We're going to be using the kinetic energy equation again. Also, the work is changing kinetic energy, and the spring equation for work. We know the mass is 0.25 kilograms, velocity is negative 7 meters per second, so square the velocity, multiply it by the mass, and divide by 2, and you'll get that the kinetic energy is 6.1 joules. The final kinetic energy is also going to be 0. We know this because it won't be moving at the bottom of the spring. Plug 0 in for the velocity and the kinetic energy, and you'll get 0. You can just cross that off and say that work equals negative initial kinetic energy. Set that equal to the initial kinetic energy and multiply it by negative 1. Work is negative 6.1 joules. Now, for this equation down here for the spring, we can say that x naught is 0 because the top of the spring hasn't been displaced yet. The k is 250 newtons per meter. And we're going to use this work that we found in the last equation and put it in for the work here. So the work is negative 6.1 joules. That leaves us with just the final x to find. Since the initial x is 0, we can cross that out. We don't need to solve for any of that. And once you plug all that into the equation, you'll get the final x is 0.22 meters.